Brachiation is the primary form of locomotion for gibbons and siamangs, which consists of moving between tree branches or handholds using the arms alone. Gibbons and siamangs make this seem effortless and are among the world's most agile brachiators. Previous work attempting to reproduce the brachiating movement, both in simulation and on physical robots exist, but capabilities are very limited and solutions are heavily engineered. We present a fully learned articulated model that demonstrates brachiation across challenging sequences of handholds that is the most capable of its kind. Furthermore, we introduce a general two-stage method for leveraging simplified physical models for reinforcement learning to learn complex behaviors efficiently in a full model. RL on the simplified model allows for fast and efficient exploration, quickly producing an effective control policy for sequences of randomly generated handholds from a sequence generator. The character is modeled as a point mass for the simplified dynamics and is a 14-link planar articulated model in the full dynamics. The policy receives information of the character and information of the next handholds in the sequence relative to its current position. Once the simplified model is learned, the full model then uses imitation learning of the motions resulting from the simplified model for efficient learning while simultaneously optimizing task and style objectives. Our experiments show that the simplified model imitation learning approach facilitates more efficient learning over the baseline. Using reference trajectory information only at training time improves learning, as shown in the curves of Experiment A and Experiment B. The best policies are obtained when simplified and full models are used in tandem at evaluation time, displayed with the curves of Experiment D and Experiment E. Refer to section 5.2 for a more detailed description of the experiments. In the following video, we show some example trajectories from the simplified model. The simplified model learns with only a simple task reward, which is a fixed-sized reward given every time a handhold is grabbed. The fact that the simplified policy can be trained with only the sparse task reward is desirable as it allows for interesting behaviors to emerge. The full model reward consists of the same task reward as the simplified model, plus an additional auxiliary reward to imitate the simplified model trajectory, and a style reward for better-looking motions. In the following video, examples of trajectories from the full train model. The brown line is the trajectory of the full character torso, while the blue line is the simplified model trajectory that is being imitated. Note that the disparity between the two is expected, given that the simplified model is approximating the center of mass and not the torso. We can see complex movements and emergent behaviors like back and forth swings to gain momentum, when needed. This sequence was manually generated to constantly measure the limit in pitch variation to climb continuously. We see that it needs to pump to reach every handhold, and as soon as it tries not to pump, it fails. This sequence, instead, has handholds equally distanced at 2.3 meters, which is over the limit seen during training. In this sequence, the full model fails, although the simplified model works. In this video, we show the capabilities of our planner. We are presented with a terrain, the brown dense line. After every handhold, the planner expands the anticipation horizon by planning for multiple time steps into the future, using both the simplified model and the value function. We can see how it avoids large gaps in the terrain and prefers to plot a constant trajectory. Using only the value function doesn't work as it fails to anticipate upcoming gaps more than 2 handholds away. Using only the simplified model doesn't work as it fails to understand what are the capabilities of the full model. If we remove the style reward completely, the task can still be solved, but the motion looks bad and not gibbon-like. If we keep the energy penalty and remove the rest of the style reward, the motion is better, but still the body swings more than with the full reward.